Hello, everybody. My name is Matt Taylor. I'm the open source community manager of the NuPIC project, which is the Numenta platform for intelligent computing. And this is Scott Purdy.
I'm Scott. I'm the primary engineer working on the project.
So we're going to run through the theory behind NuPIC, which you caught a glimpse of this morning when Jeff gave his keynote. We're going to go a little bit deeper, just enough so you can kind of understand how we set up the software. Scott's going to talk about the actual open source NuPIC project. And then I'm going to talk a little bit about our growing community. So first off, who has read this book on intelligence? A few, awesome. Who's heard of it at least? Okay, so this is a great place to go to get a really nice layman's term example of the things that we're going to be talking about. It's a great introduction to these theories. So I wanted to throw that out there. Go ahead. So we're going to talk about the cortical learning algorithm, which is really the meat of the NuPIC project. As Jeff was talking this morning, if you take a small slice of the neocortex, it looks like this. Go ahead. And what it really consists of is a cellular structure with columns and layers. Each one of these little circles in this box represents a neuron. And one thing that's a little different in our algorithms than most neural networks or standard artificial intelligence algorithms is that we really try hard to simulate the way neurons really work and all of the different synapses and connections that neurons make between each other. So that's kind of a core piece of how this technology works. So at a high level, the part that's within this box here is really what the cortical learning algorithm is all about. We're taking a chunk of the neocortex and we're simulating it in software, and we're pushing data into it in the same way that your senses push data into your neocortex. And that is the CLA, the cortical learning algorithm. So we have this structure of cells that we set up, and then we let the connections establish as data is passed through them.
And in the bottom right, you can see our model of a neuron. We're not going to go too detailed into the algorithm, but
it's complicated. The way neurons connect is not easy. It's not just a simple connection. Connections are established and they're diminished, and it depends on what they're seeing. That's how patterns are recognized and patterns are forgotten. So we really can't go too deeply into how this works because it's hard to explain. It's sophisticated. What we can kind of tell you at a high level is that these properties emerge from this algorithm, like sequence memory can make simultaneous predictions as it's seeing patterns. It has a very high capacity. So just like your brain can handle high capacity data throughput, this algorithm can also handle it in the same way. It learns online over time, and we'll show some examples of that, and it's fault tolerant. So meaning if some of these neurons die, if the CLA goes on a bender some night and some of the neurons go away, it can still recognize the patterns, and it's not going to just fall over. So what does it do? Well, like I said, it accepts streams of data. So you have to establish a way to push data into the algorithm. And it likes fast temporal data. So the faster and the more time-based it is, the better. It learns the spatial patterns within the data, and it also learns the temporal patterns over time within the data. And it does that by creating a model of the data in the form of connections between the artificial neurons within the CLA. It provides inference or pattern recognition, and the way we do that is through predictions. So it can give you predictions about what you tell it you want it to predict as the data is coming through, or anomaly detection. It can tell you how unexpected is the data that it's currently seeing. A little bit more of a taste. One of the key concepts underlying here is sparse distributed representations. I'll let you explain that.
Sure. So again, sparse distributed representations could be kind of a talk on its own, but just a couple properties about it that make it really powerful that I wanted to mention are, so the key idea is you're representing data with a lot of bits with very few of them active at any given time. And you can think of a bit here as a cell, and so you have very few firing at any given time. And these representations are learned from the characteristics of the data. So each bit has semantic meaning, and the semantics of a specific value are distributed across that representation. So what this means is you can flip one of those bits, and you largely have the same semantic meaning. Unlike traditional computer representations, where if you flip one bit in an integer, you could get a wildly different number. And so this is a fundamentally different way of representing data than traditional computers represent data. And so this is really powerful. And in addition to that, the way that we're organizing the cells and the neurons into columns and into layers is just like the biology of your brain.
I like to emphasize how different this is, in that what you're doing right now in your brain, you're not writing images to disk within your brain the same way a computer would do. It doesn't work like that. Your brain, the data from your senses is passing through your brain, and your brain is maintaining a representation of the patterns that it has seen over time. And it does that with sparse distributed representations. And what this really is the strength of connections between all the neurons in your neocortex. That's what holds all of your memories, all of your intelligence, everything. And that's really what we've created, a small piece of your neocortex, in that it can recognize those patterns without ever writing any of the data that it ever sees to disk, and it can tell you about what it's seen in the model that it creates. This is a deep topic. We've got a 64-page white paper about cortical learning algorithms, and it goes into sparse distributed representations. You can go to Numenta.org and download that white paper and take a read. It's thrilling. We also have, right now, an application that works with this code base. Numenta also does business as a company called Groq. We have a product called Groq. It's a cloud service-based product, and what it does is similar to what I've been saying. It accepts high-velocity streaming input data, and it has Newpick running inside of it. This is the exact same code base that you can go download from GitHub today we're using within this commercial product. Initially, the focus is on industrial automation, IT applications, but there's no reason to restrict it. One of the main reasons that we wanted to open source the core algorithms behind this product is because there's lots of different things that people could be doing with this that we don't have the time or resources to do. Things like vision processing, robotics. There's lots of different directions that this could be taken. If we had a novel way of introducing sensory motor integration, you could do some really interesting thing with robotics. Audio processing, several people have talked to us about natural language processing, et cetera. So we want people to take this code base and run with it and try and do something interesting with it, because we feel like it's really powerful, but it's very generic, and so it's hard to investigate all of these avenues. So we're going to give you a little demo first. We had a hackathon back in June. It was a really fun event. We had 25 or 30 people in our offices in Redwood City, California, and about 7 different demonstrations at the end of a 24-hour hackathon. And I'm going to show you one of the examples that a group created with Newpick. This is, I forgot their names. They're a group of Stanford grads. There it is. Danny Bankman, Stan Nikoloff, and Jin Pan. So I wanted to say that. So what they did was they decided they were going to teach the CLA a song. And keep in mind, this seems like a trivial application. Any of us could probably write something that could take a song and repeat it back. But we're using the same biological structure that's in your brain. So we're basically taking an empty brain, and we're going to push this song, or encode some song in a way that the CLA can understand it, and then tell it, show it, let it listen to that song a certain number of times, and then ask it, okay, play back that sequence again. So we're going to play the original song, and I want you to raise your hand when you recognize it, when your brain recognizes it. You can't have recognized it yet. There we go. So we're all well-educated folks in here. Somebody recognized it just from the sheet music. That's impressive. Okay, so that's what was encoded and given to the CLA. So this is what the CLA thought the song was after it heard it 10 times. So basically pushed it through 10 times and then asked it, give me a prediction for the whole cycle that you just heard 10 times. So let's hear it. Did you hear that? It's in the right key, but it's not good. So, it's not, but it only heard it 10 times. And it's never heard this song before. It's never heard any song before. It's never seen anything before. It's just an empty structure. So let's see what it sounds like after 20 repetitions. It's getting there, right? I mean, there's a bit of a false start in the beginning because it didn't recognize where the beginning of the song was. It just knew it just knew you wanted it to predict the next cycle. It hadn't recognized where the cycle began and ended yet. Okay, so they kept going until they found a point where it behaved a little better. So this is after 25 listens.
It's pretty good, Matt.
It's perfect, Scott. It didn't mess up one thing. So after 25 repetitions, it got it down pat. So you might think, oh, this isn't so impressive, but think about how it's doing it. It's doing it the same way you memorize songs. It's using the same biological principles within your neocortex to do this. So I think that's a powerful example. This is sequence memory, and it's online learning. It went from 10, it had a crappy representation of the song, to 20, it got a little better, and it nailed it after 25. So it's memorizing these common patterns. It doesn't store data. It remembers it. It remembers the sequences. So this is just like your brain does it. That's my main point. Scott's going to go into a little bit of the nuts and bolts of the code base now.
Yeah, so I hope that gives kind of a high level about what the algorithm is, what it does. But we want to give you a really hands-on sort of, if you want to use this for your own problem, or if you want to get more involved and learn more about this, what do you do? Where do you get started? So first off, just some high-level points. This is a Python API right now. Some of the code is implemented in C++. And we're hoping to move more of the code into C++ so we can build bindings for other languages. But right now, it's a Python interface. It's up on GitHub under a dual license. So if you get it off GitHub, it's going to be GPL v3. If you don't want the restrictions of that, you can come and talk to us. And we have Travis CI integrates really nicely with GitHub for continuous integration. So external contributors or internal contributors, when you submit a pull request, it'll automatically validate against our test suite. So that works really, really nicely, and Matt will talk about that a little bit later. So right now, I wanted to go through an example with a real data set and show you sort of what it would look like to get started. So first, I'm going to switch over here to a web browser and go to numenta.org. This is sort of the entry point for the open source project. There's a lot of resources here, but the one that I'm going to click on here is click through to GitHub. This is the GitHub project, and you can check out the code just like anything else on GitHub. And then check out the README for the installation instructions. And once it's installed, there's some examples, some tests and examples that you can run to make sure it's installed correctly. And this one at the bottom here, I'm going to walk through sort of how you would create that. So switch back to the slides. What does the data look like, first of all? So this is just a plot of just a few days of the data. This is building energy consumption for a gym. And so this is measuring the electricity usage in the building. And it's sampled once an hour. So there's 24 data points each day. You can see here about 4 days. During the day is when you have the big peaks. And then there's also a little overnight spike when the cleaning crew comes in. So this is a nice data set because, first, it's a really important problem. Electricity is one of the few things that you can't store very easily. It's very expensive to store energy, so you really need to be able to predict your usage well so you can generate the right amount. And it also has very clear temporal patterns. It has daily patterns, it has weekly patterns, and you'll see how that works in the algorithm. So first I'm going to kind of walk through the code here. If you have it installed, the first thing that you're going to do is create an instance of our model, and that's generally, we use about 64,000 cells, neurons, essentially, in a model. And so all a model is like one instance of that. And it starts out knowing nothing when you create it. And you pass a few model parameters in, and I'm not going to go into those, but you can specify how many columns you want, how many cells per column. And one of the key things that you're going to specify in here is the encoders. So in this data set, we have a timestamp and a consumption field for the energy consumption. And so you need to tell the model what types of values those are. So it knows how to turn those raw values into binary representations that the algorithms understand. You also specify in there the number of steps that you want to predict into the future. So I've specified in there 1 step and 5 steps. And there's some other parameters in there that I don't have time to go into. But there's information about that more in the project. And we have a set of encoders that this ships with. So for most data sets, you should be able to use the existing encoders for scalar values, categories, and timestamps. And then once you create the model, you enable inference, tell it which field you want to predict. So we're going to predict the consumption for this. So then you have to get the data in. In this case, I'm just doing it from a file, but it doesn't really matter where you get it from. You can get it streaming from sensors or however you want.
This is Python, by the way.
Yes, and this is Python code. And so once you have the data, you just have to put it in the right format. The model is going to expect a dictionary that maps from the field names to the values. So once you get it in the right format, you feed it into the model, and you get back a result. So what does the result look like? So this is an instance of a model result. And the most important thing in this, when you're doing a prediction problem, is the predictions that you get out of it. So here you can see that it's predicting about 5, a value of about 5 for the energy consumption. And it's giving it about a 70% probability of occurring. And this is in the 1-step section. So this is saying 1 step ahead, it's predicting the value of about 5 with about 70% likelihood. And then you can see there's a few more predictions there. I actually took about 5 of the predictions out of the 1-step section just so I could fit everything, and those were between 1 and 2% likely. And then similarly, in the 5 steps ahead section, we get predictions, so about 38 with a little over 22% likelihood, and then there's a number of other predictions there. And you don't always need all of those. You don't always need all those different probabilities. If you just want the best prediction, there's a convenience key in here that will just give you the best prediction for each of your steps.
So to be really clear about this example is something that you check out when you get the project from GitHub. The data is coming from a CSV file. It's just timestamp energy consumption. And all that code is doing is just reading that file and line by line, pushing it into the algorithm. And every time you give it a value to process, it gives you back one of these model results and tells you, oh, you set me up to predict 1 hour in the future and 5 hours in the future. This is what I think is going to happen.
Yeah, and this is a real data set from a real building. So let's go ahead and take a look at this. I'm running the code that I just showed you, but there's some extra code in there for plotting it, the license at the top, things like that. But basically the same thing that I just showed you. So here I'm going to plot the predictions 1 step ahead. And the first thing that you'll notice is, so the actual values are in blue, the predictions are in green, if you can see that. The first thing you'll notice is the predictions are trailing by an hour at the beginning. And that's because this model doesn't know anything. Just like in the music example, this is a completely new model that's never seen any data before. So it doesn't really know what to predict. So it just predicts the value that it just saw. But as it learns the sequences in the data, you'll see it start sort of trying to make predictions. And over time, this is going to get better and better. And this is completely online learning. So with each new record that it gets in, it's updating its internal representation and giving you predictions back. So we should see here, one thing that you can take a look at to sort of see it learning is when the blue value spikes at the beginning of the day, that sort of that uptick, it's been trailing all this time. And just right there, that most recent uptick, it predicted it was going to go up when it actually did. And there it got it the second day. So now it's actually doing pretty well after about a week of data.
And one of the interesting things about this is this data has a lot of temporal patterns in it. It's got daily patterns, it's got weekly patterns, it's got monthly patterns. So for the CLA to really learn those, it needs to see those patterns repeated over time. So in order to get a really good representation of this data, you need a lot of data to kind of feed it through so it can learn what it's trying to predict.
But we also got 5-step predictions. So let's take a look at those. And again, this is starting with a completely new model. So we're going to have those trailing predictions. They're going to start out trailing by 5 hours because it's predicting 5 hours ahead. But in the same way that it's making 1-step predictions, it's making 5-step predictions, and we can watch as it learns the patterns and starts making predictions. And there, I think it gets kind of lucky on the 3rd day there. But another interesting thing about this is if you let it play out for long enough, you'll see that the data changes over time. And because it's fully online, it'll update its internal representation, and it'll see those new patterns and make predictions accordingly. So
I'd like to see an example of that, Scott.
Yeah, so it's kind of getting a little mixed up here, but I've taken, we have a couple images here.
Five-step predictions are harder than one-step predictions. So I know what I'm doing in 5 minutes, but I don't know what I'm doing next week at all.
So these are two captures from this data set, and these are from two different spots in the data. And what you can see is in the top one versus the bottom one, it's kind of hard to tell, but the bottom one, the energy consumption is a lot higher during the day, each day. So just I don't know if they have more people coming to the gym then, or they change their air conditioning, it's the summer or something. But the energy usage is higher. And then also within a day, in the top example, during the day, there's sort of a zigzag at the top. And then in the bottom one, you sort of have two little mini peaks within the day, one towards the beginning of the day and one right at the end, right before the energy usage drops off for the day. So you can very clearly see that the patterns have changed. And this is where the online nature of the model really comes in handy. You don't have to create a new model. You don't have to change the parameters. It's just going to see that the data is changing, and it's going to learn the new sequences and update its predictions accordingly.
What I think is cool about this is what you're looking here is really kind of group human behavior. I mean, this is energy consumption from a building, but it's a gym where people are going and working out. So it's not going to stay constant. People are going to change. Populations will change. It could be that last spike that's occurring on the bottom, at the end of the day in the afternoon, could be they added a few more classes. The gym added more classes. There's more consumption. That's going to change over time, and the CLA will pick that up. You don't have to retrain it. If it sees the pattern enough, it will remember the pattern. If it doesn't see patterns that it was remembering anymore, it will forget them because the connections between the neurons diminish.
Yeah, so that's sort of it for this prediction problem. In addition to prediction, the CLA can do anomaly detection. And so in this example I'm showing here, we're using the CLA to detect anomalies in a large piece of machinery, and we're getting a sensor reading that has the gear bearing temperature. And we want to use that value to tell us when something's changed, when something looks unexpected. And we're going to use that as a signal for when we maybe want to do maintenance on this. And this, again, is an important problem. This is very costly if the machinery fails. So if they can sort of detect ahead of time when they need to do maintenance or order new parts, they can do that. So I want to point out a few sections in this data. The blue line is the gear bearing temperature, and the red line is an anomaly score that we get out of the model. And the anomaly score is from 0 to 1, where 1 means it was completely unexpected, and 0 means it was perfectly predicted, looked completely normal. So in this first section, you can see the anomaly score is actually pretty high. It's pretty spiky and goes pretty high. And that's because we started with a fresh model. It didn't know anything about the world. And so all the new sequences it was seeing looked unexpected.
To a newborn baby, everything is anomalous.
Yeah. So, and then you can see the section after it, sort of the second quarter of the data, the anomaly score settles out. And it's seeing the same patterns. Everything looks pretty much okay. But then about halfway through the data set, the patterns change, and the anomaly score spikes up again. And what's interesting about this is especially that first anomaly score spike in that section, the data values aren't outside the typical range. Traditionally, when people do anomaly detection, the first thing they'll try is just thresholding the values. When it goes outside of this range, then I'm going to fire off an alert. But in this problem, you can't do that. It wouldn't work. And so the CLA's ability to look at the temporal patterns and see when something's changed allows it to give you these signals when you wouldn't be able to get it from a lot of other methods. And then just as an illustration of how the anomaly detection works here, we took this same section of data highlighted here, and we cut and pasted it again. So the model saw the same section of data twice. And what you can see is the anomaly score isn't as high in the second time that it's seen it. And that's because it's doing online learning. And so when it sees the sequences the first time, it learns them. And so they're sort of predicted the second time. It doesn't look as unexpected when it sees it again. If you don't want this, you can turn learning off. But so that's basically it for the anomaly detection example. I wanted to quickly review the examples that we just gave. So for the prediction problem, We were streaming energy consumption data in. It was learning the spatial and temporal patterns, and it created a model of that in the same way that your brain does. And it was performing inference and using that to make predictions about the future. And then in an anomaly detection example, we were using it to detect anomalies. So that's that. Matt's going to talk a little bit more now about the community that we're building around this, and if you want to get more involved, how you can do that.
So let me bring up one point first. So I think there's many ways that this open source project is different than others, but one thing that I like to point out is, go ahead, that we're open sourcing something that's at the core of what this company is all about. A lot of other companies that might have a commercial product, and they want to open source something, they end up open sourcing their tooling or something like that. Something that they know they want to help others. They say, well, we built something awesome that helps us build what we sell. So we want to make that available to others to help them. But we're open sourcing the engine. I mean, this is really the core of what we do. So I think that's important to point out, that our product is built directly on top of this. And we want to share this with people because we think it's a good idea. So we also have one single source tree. That's kind of another thing we debated a lot about, whether we should put something out on GitHub and then have an internal repository that we kind of merge in once a week, once a cycle, whatever. And we decided after a long debate we're not going to do that. We're going to have one single source tree. What you get on GitHub is what we're using right now. So you can see us developing daily on there, and you can see our community members also submitting pull requests. The model that we've adopted gives us a master branch that's always green, so anybody can go grab that and be confident that at least the continuous integration builds pass. And because we do all of our testing within pull requests. We use GitHub and Travis CI. Does anybody else have love for them in here? Great tools, great tools. So we use those extensively. Their status API and the Travis CI build integration. We took full advantage of those things, and I love these guys. So our community currently is very young. We open sourced June 3rd with a very small amount of fanfare. We just put up a blog post and put our code on GitHub. We currently have, last I checked, 44 contributors that have signed our contributors license. We have about 160 members of our mailing list, but it's for that number, there's a lot of mailing list traffic, 10 messages a day or so. And a lot of it is discussing the theory of this. What can be done with this? How does this work? There's lots of high-level, really interesting concepts in there. And our founder, Jeff Hawkins, participates a lot in these discussions. So it's a very valuable resource if you want to learn more about how this stuff works. So I'm also going to show you real quick our public issue tracker, because I like this because you can see what we're working on. So we do have a public Jira instance. So this is what Scott and I and another engineer on the team are working on right now. This is our current sprint. I'm trying to get my CEO to write a blog post, and it's not happening. But so you can see what we're doing. We want you guys to get involved. We're looking for community involvement. We think this is novel stuff, and we'd really like to get people excited about it and try and figure out what can you do with it too. We have an IRC channel as well. We just did a hackathon. This was really fun. We did this last month. Like I said, we had 25, 30 people come in. We've got a blog post with we taped the entire thing, all 24 hours. And so I've got each of the demonstrations that people ended up with at the end in this blog post. So you can go and look at them. So things like robot movement. We had somebody put CLA and work with the robot. Someone was using IR sensors to predict human movement. Someone was predicting weather. Someone actually got gyroscope information from a mobile phone and did jumping jacks and squat thrusts, fed that through the CLA, and had it predict what movements he was doing. Interesting. And somebody else had it win a game of tic-tac-toe. I don't know how it works. And there's lots of things you can do with this. So we want you guys to get involved. The number one thing to remember is numenta.org. That is the portal. You can get everything, all the information you want there, hopefully. And if you don't, there's an email address you can email us about and tell us what's wrong. We have got the public issue tracking, and we also have a task list for newbies. If anyone wants some low-hanging fruit, We've got some documentation tasks, some research tasks, that sort of thing that we make available if you want to get started with us. We will have another hackathon this fall, probably October, in San Francisco. I haven't nailed down the venue yet, but we do have an events page on Numenta.org, so you can always see that. There's an RSS feed as well. There'll be a news post, etc. So please check in later, and hopefully those events data will be posted. If you want to learn more about this, I would highly suggest that you look into that CLA white paper. That's probably the best resource to understanding the underlying algorithms and how this works. If you don't want to go that deep, On Intelligence is an easy read. It's cheap. We've got a birds of a feather session tonight. If you come and tell me that you were here, and give me a contact information, I'll get you a free ebook. You can join our mailing list. Like I said, lots of good discussion going on there. The lowest friction point of entry is to go watch videos on Numenta.org. I've collected several videos of Jeff, his past talks at like Strange Loop. He did a Google Tech Talk recently that was really well received. And we also have some of our engineers actually doing some whiteboard sessions explaining how the CLA works in different scenarios. So very informative stuff if you just want to veg out. Mention birds of a feather. Come talk to us, please. We're going to be in E114 tonight at 7 p.m. Jeff will be there. Our VP of Engineering, Subutai Ahmed, will be there. Scott and I will be there. And we're going to have a few community members that participate in our mailing list that are also coming to meet and greet with us. So we'd be more than happy to have you come and say hi. So that's it. We do have some time for questions, and we will be outside of the ballroom afterwards if you guys want to talk to us. But it looks like we have some time to take any questions if you have any. Sir, can you come up to the front so I can hear you? Yeah. So can you repeat the question?
Yeah, so the question is that we showed examples with one-dimensional data. Can you give it multi-dimensional data? And can you vary the dimensions based on the context? Is that? Can you compartmentalize learning so it can recognize the context? Yes. So you can give it multi-dimensional data, but with each record that you feed in, it's going to expect each of your fields to be present. So I guess
these examples aren't necessarily typical, but they're simple. So in a real-world case, you're probably going to have many factors that could contribute to the value that you're actually attempting to predict. So you probably want more than just, a timestamp and a value that you're predicting. You want other factors involved. You want to feed other data into it. And the CLA will take into account the patterns in that data when it's making predictions on the field that you want to predict, if that's what you're talking about when you say multidimensional. So your other question, I'm not sure about.
Yeah, I don't fully understand what the compartmentalization.
You can turn learning on and off. I don't know if you can do that live or. Yeah.
Perhaps we can.
But we probably need a deeper conversation on this. Why don't you talk to us afterwards, and we'll try and help.
Yeah, the short answer is yes.
There.
Yeah. So the question is, can we give examples of real-world examples of usage of this? So we have a commercial product called Grok, and Matt mentioned earlier, we primarily are using that. We're focusing on energy. So predicting meters. We're also doing server data.
Yeah, it's really good with machine-generated data. Yeah. So anything that comes fast and consistently, and you find something in there that you want to predict a value, and it does well with that temporal type of fast temporal data. But as far as real-world things, we only have this one product that is currently using NuPick. There's no other that I know of. There are other implementations of these algorithms that I know of, but no products that I know of that are currently using it except us. Right now, we're focused. We're very focused on industry automation and focusing on energy sector and IT applications. And I don't know how much I'm supposed to say about it, though. Yeah. So the question is the number of cells in the network tunable? There's a lot of things that are tunable. So I think the hardest thing about setting up a problem with the CLA so that you get a solution is coming up with the proper parameters just for the setup, for setting up the blank, the blank slate that you're going to be pushing data through. And one of those variables that you can set is the number of columns, right? Also, you can set. You should talk about these.
Yeah, so you can set the number of columns, the number of cells per column. We typically always use 2048 columns with 32 cells per column. It works pretty well for any problems similar to what we've shown. And but you can change them. If you want to do vision, you're probably going to use different numbers. We also only do one region at a time. We don't do hierarchy right now, but that's an area for research.
Yeah, one of the reasons we want to open source it, we'd like other people to attempt that. And just as a reference, our typical setting is around 64,000 neurons when we typically run the CLA. Your brain has 60 billion neurons. So this is a very, very, very small part of the neocortex that we're actually modeling here. Jeff. It's not sensitive to those numbers.
Yeah, so you can change the columns and the number of cells, and it doesn't change the results very much. Yeah, within bounds. In Gray, Purdue? Yeah, so the question is, have we tried it on things other than time series prediction and like specifically classification type problems? We have, and it does have some classification capabilities, but typically we find that the value prop for this is that it is really good with time series, temporal, streaming temporal problems. Specifically, we try to find problems where it's machine-generated data, and where we can automate the actions that we take based on the predictions or anomaly detection. So the question is where this algorithm would do better or worse than traditional neural nets. I don't think I can answer that very well.
You're unqualified to answer that question?
Yeah, I don't know.
I am. Sorry.
Subhatai, did you?
So we only have another minute. We should probably take that conversation outside. Let's get a couple more questions if there are any.
Yeah.
You're standing in line there. Yeah. Right. Right. So the question is there a good way to allow a model to go outside of itself to find information? That implies an action. So that implies sensory motor integration, which is a part of the brain that we currently are not modeling. No? Okay, Jeff, do you want to answer this question? Okay.
Yeah.
We only have a few more seconds left, so we should probably let's take these discussions outside. We can get Jeff and Subhatai involved in them because they're the real experts. I'm just a mouthpiece, really. So thanks a lot, everybody. We'll be outside if you want to talk.